Hello, and welcome to this lesson on describing relationships from graphs. In this lesson, we're going to be talking about having a graph of a function and being able to put some meaning behind what the labels mean, what the graph looks like, basically being able to tell a story from a picture. Okay, we can see the essential question says, how do I describe fundamental relationships from graphs? Did you know that functions and relations, they kind of sound confusing, but it's just showing a relationship between two values. Rainfall over time, money made per year, if a plumber charges $36 an hour, hot dogs eaten per person, corn yield per acre, all these sort of things, all of these are relations, and they could be graphed. They have an initial value, they have a rate of change, and so they all could be functions. They're not necessarily all linear, but they all could be represented as functions. There is no new vocabulary in this lesson, so let's get to it. So here we have a couple of graphs, and what we'd like to be able to do is describe what's going on in these graphs. So I'm looking at this first graph, and the first thing I notice here is this is linear. Sorry about that. So this is linear. Let me mute this one more time. There we go. Now we should be in business. So my graph is linear. It's a straight line. Okay. What else do we notice about it? Well, I notice that it is going up over time. It is increasing or has a positive slope. I'm going to put both of those because they're interchangeable, and there are times where the description might use one or might use the other. Okay, so I have it's linear. I have that it's positive, it's going up, it's increasing over time. That's really about it. I mean, it's definitely a function. It's a linear function. Okay, letter B. I can see that this one is nonlinear. I can see that it is decreasing / it has a negative slope. But I'm going to see with kind of decreasing for now. So it's nonlinear, it's decreasing, but it's more than just nonlinear and decreasing, because just saying nonlinear decreasing could have a couple different meanings. It could look like this. It could be, kind of like that. That one's kind of more linear. So how is it decreasing? Well, at the beginning, it's decreasing not too terribly fast. But at the end, look at it. It's almost straight up and down. So this guy is decreasing faster over time. So it's nonlinear. It's decreasing faster over time. And this bottom one, I guess, doesn't always have to be the time variable, but it kind of gets the idea that it's decreasing faster and faster and faster as we go across the x-axis. So it starts off slow, and it gets faster and faster and faster. And by the end, it's decreasing very fast. Okay? One more for me and another for you. So this guy here is... well, there are pieces of it that's linear, like from here to here, that's linear, and that's linear. That's not. But overall, from beginning to end, this is not a straight line. So we would say this one overall is non-linear. It is not a straight line from beginning to end. Now, as far as, is it going up? Is it going down? Increasing, decreasing? Well, it's doing a little bit of both. It's both increasing and decreasing. There are parts right here in the beginning where it's increasing, decreasing, and decreasing. This is increasing linear. This is decreasing at a constant rate. We'll call that linear as well. And we're also now decreasing slower and slower over time. We're going to get to a problem later on soon where we're going to be describing it, breaking it down into individual sections. But for now, the whole thing, we'd say this whole thing is nonlinear, and it's both increasing and decreasing. Okay, so I would like you to take letter D here. And pause the video and try those, and put down any descriptions you can for letter D. Go for it right now. All right, so you should have said nonlinear. It is nonlinear. And this one is increasing. Increasing how? Is it because it's not a straight line. It's increasing kind of slowly at the beginning, and it gets faster and faster and faster. So I'm going to put it's increasing faster and faster. Whoa, and faster. So it's kind of like increasing faster over time. It starts off slow and it's increasing faster and faster and faster and faster, and it's going to keep kind of going up at this increasingly fast speed. Letter E and F. Go ahead and pause the video and try these two right now. All right, letter E. This is nonlinear again. And this one is both increasing and decreasing. There's some uppy parts and some downy parts. So it's increasing, decreasing, increasing. So I'm going to put that it's increasing and decreasing. Letter F is low, not nonlinear. It is linear. It is a straight line. And he is strictly just decreasing. Because he's decreasing at a constant rate. That's another way we could say this. It's linear, decreasing at a constant rate. It's decreasing the rate, the slope is the same everywhere. So we could say it's decreasing at a constant rate. Now we can actually take this sort of thing and we can break it down a little bit. So this one graph is made up of a bunch of different parts. And there are times where maybe we're asked specifically, like, hey, between day 0 and day 1, what's the temperature doing? So this graph is showing over the course of 5 days, 1, 2, 3, 4, 5 days, what's happening to the temperature outside. Okay, so between days 0 and 1, between 0 and 1, what's happening to the temperature? Well, the temperature is decreasing. It's going down. And we can keep going. So between days 1 and 2, 1 and 2, in this kind of next block, what's happening? Well, from beginning to end, it's overall, it's increasing. I mean, there's this little bit of a dip here, but overall, it's gone up from, 15 degrees up to 30 degrees. So temperature is increasing. Between days 2 and 4, the temperature is doing what? Okay, so here's 2 to 4. So what's happening between here? Well, it's pretty darn flat. I mean, there's a little bit of a dip in here, but overall, the temperature kind of remained the same. How would we say remained the same using kind of math terminology? Do we have a word that means remains the same, doesn't change? We do. It's the word constant. Something that is constant in math doesn't change. Typically, it also means there's no variable. So like in the expression 3x plus 5, this 5 is considered a constant because it does not have a variable attached to him. This one can change. This one will never change. He is a constant. And lastly, between days 4 and 5, in my last kind of block of time of this problem, what's happening here? Well, it starts off kind of constant and then it starts decreasing faster and faster. And I can even add in a little extra detail. Like the more detail you add makes this better. So I could say between days 4 and 5, the temperature is decreasing, and I can say faster and faster. Between days 0 and 1, the temperature is decreasing. Honestly, it's fairly linearly. Like it's a fairly straight line. So I could say decreasing at a constant rate. I mean, all these little details take your answer from being an okay answer to a really good answer. And that's kind of what we're trying to get to. We don't want just a basic answer. We want as good as you can get. Between days 1 and 2, it is increasing. Is it increasing faster and faster? Is it increasing at a constant rate? Increasing slower over time? Not really, because there is some downy and there's some uppy. So overall, I think we could only really just say it's increasing. It's not at a constant rate. It's not like a straight line. It's not increasing faster and faster over time where we have a shape kind of like this. It's not really increasing slower over time where we have a shape like this. So it's just kind of increasing. We can't really add more detail to it. Is the function represented by the graph linear or nonlinear? So this one up above, this same graph here. Do you believe that to be linear or nonlinear? And explain your reasoning. Well, it is very, very, very nonlinear. And to explain our reasoning, we'd say, well, it's not a straight line. Whoa, what am I writing? Let's try that again. It's not a straight line. So it's definitely curvy because it's a curvy. It's non-linear. It goes down, it goes up, it goes flat, it goes down. It's not linear. It is not a straight line. So that function in general is non-linear. Now, the third thing we should be able to do is we should be able to make a sketch, a rough sketch. We're not looking for perfection. We're looking for about. It should look right. So sketch a possible graph for each function. Tell whether the function is linear or nonlinear. Or tell whether the function is increasing or decreasing. Okay, that seems easy enough. So James wants to buy some grapes from the store. Each pound of grapes costs the same amount. Now you might be looking at it going, how in the heck am I going to graph this? Well, there's a few things we can do. One thing I like to do is I personally like to make a table. Tables work very well for word problems and functions and stuff. So he wants to buy some grapes. Each pound of grapes costs the same. So we've got grapes and we've got our cost. So let's say he buys 1 pound of grapes. Let's make up a cost. It doesn't matter how much they cost. Let's say they cost $1. If he buys 2 pounds of grapes, how much is that going to cost him? $2. $1 each. If he buys 3 pounds of grapes, that's going to cost $3. And 4 pounds of grapes is $4. Because every pound of grapes costs the same amount, we kind of get this nice linear relationship. It's increasing at a constant rate. So now I can label grapes cost 1, 2, 3. I don't even like doing that. 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10. I don't like to label every single line because, well, my handwriting's a little sloppy and it makes it uglier if I have numbers all in here. They just look very jam-packed together. So I like to label every other line. It just makes it prettier for me. Now, if I go through and I graph the points I have labeled, 1 pound, $1. 2 pounds, $2. 3 pounds, $3. 4 pounds, $4. We can kind of get a feeling of the line that we're making. So this is a linear relationship because each pound of grapes costs the same. It increases at a constant rate. Now this is also increasing because our line is going up from left to right. This is increasing. The more grapes you buy, the more it's going to cost you. Okay? So making a table here was a very good strategy that helped us understand and make sense of the problem. Letter B says, Sam's company paints walls. The more people he puts on one job, the less time it takes. Show the amount of time for a job with X people. Okay, so we know that the x variable is our people. It actually told us right here, x people. So I'm going to label people. And I can even start going 0, 2, 4, 6, 8, 10 people. And the other variable is the amount of time. That is our other axis. And if you want to be more specific, we can say time in hours. And 0, 2, 4, 6, 8, 10. Now, I don't really know what this is going to look like, but I can make a table. So let's say here, let's play pretend here. We've got, well, X people and Y hours. Let's say we have a wall, a big wall. It would take one person, let's say 10 hours to paint. Now, if you had 2 people painting that wall, how long would it take? How long would each person have to work? Well, each person would work for 5 hours. If you cut it in half and one person paints one side, one person paints the other, you got 5 hours and 5 hours. If you have 3 people painting the wall, and they're each, I would assume, painting roughly equal portions and painting at the same basic speed, how long would that take? Well, it would be same 10 divided by 3. It would take about 3.33 hours. If you had 4 people painting the wall, 10 divided into 4 chunks, each person would paint for about 2.5 hours. I want to fit one more in here, so I'm going to make my table a little bit tinier. If we had 5 people, each person would only work for 2 hours. So if I had 5 people and I broke this wall up into 5 chunks, 1, 2, 3, 4, 5 chunks, each person would paint for about 2 hours. That still totals up to the 10 hours total, right? 2, 4, 6, 8, 10. There's still 10 man hours there. It's just divided among more people. Now, why do we do this? Well, check out when we graph this table. So the first one is 1 person, 10 hours. 2 people, 5 hours. 3 people, 3.3 hours. 4 people, 2.5 hours. The one down here is 5 people, 2 hours. Now look at the dots we have. A straight line is not going to do a good job. A curvy line would. And if I just kind of start connecting my dots and I kind of extend here a little bit, I can see, ooh, I got a little wonky in the end, but we can see the kind of the shape it's making. It's not a straight line. This is non-linear. And the table is what did the job for us. Actually thinking through a scenario and putting out a picture maybe and making a table, that helped us understand. This one is decreasing. And how is it decreasing? Well, it's decreasing slower over time, slower and slower. Like right here, it's decreasing really fast. It's almost straight up and down. And then it decreases slower and slower and slower. And right now it's barely decreasing at all. So I'm going to say this is decreasing slower and slower. So that gives us a very good graph and a nice description of what's going on. If you could please, could you pause the video and try this letter C on your own? I recommend making a table. I recommend labeling your X and your Y axis and plotting points and maybe even drawing a picture of stuff. Okay, so go ahead and pause it and do this one right now. All right, it says a car traveling at a constant speed consumes about 2 gallons of gas per hour. That sounds important. 2 gallons of gas per hour. The car starts with 9 gallons of gas before it leaves for its trip. Okay, so our variables are going to be our gallons of gas and the hours we're driving. I'll tell you, well, I'm going to take a good guess that the hours is going to be our x variable and the gas is going to be our y variable. And what makes me say this is time, the hours, is never the dependent variable. The independent variable is always your x. Time is always independent. So the gas you're using depends on the time, how long you've been driving. So the gas is the dependent variable because it depends on the time. So we're going to have hours and we're going to have gallons. So if we start hour 0, we have 9 gallons of gas. 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10. If you've been driving for 1 hour, how much gas do you have left? Well, you'd have 7 gallons. You used up 2 of them, right? 2 gallons per hour. If you drive for 2 hours, you would now have 5 gallons. If you drove for 3 hours, you would have 3 gallons. If you drove for 4 hours, you'd have not 2 gallons, 1 gallon. And if you drove for 5 hours, you're going to be out of gas. So now we just graph these points. 0, 9, 1, 7, 2, 5, 3, 3, 4, 1. And we can see how this works. We can see that this is a linear function. Oh, too many letters. It's linear and it's decreasing. And we could also add, if we wanted to, it's part of linear. We could say decreasing at a constant rate. That doesn't hurt. It makes your answer a little better. It doesn't hurt to say. And there we go. All right. Letter D says each time a set of cells divide, it doubles the number of cells, which is true. When a cell divides, I think it's called mitosis. When a cell divides, it splits and it doubles how many there are. So if you originally start with like one big cell and then it splits in half, then you have 2 cells, and then each of those split, and then you'd have 1, 2, 3, 4 cells, something like that. So if there were 5 cells, after they divided, there would be 10, then 20, then 40, etc. Show the number of cells after x divisions. Okay, so our x variable is our divisions. 0, 2, 4, 6, 8, 10 division. And we want to show the number of cells, so that would be our y variable. Now, how we label our y-axis really depends on how high our cell number goes up. Like, if I want to get up to 50, I would need to not count by 2s or 1s. I'd count by 10s or 5s or something. I think what I'm going to do is I'm going to count by 10s. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That gives me plenty of room to grow. So now let's say I start with, at the beginning, let's start with 5 cells. Let's just do the one it says here. So if there were 5 cells, after they divided, in one division, there'd be 10. If they divided again in a second division, now there'd be 20. In a third division, now there'd be 40. I'm actually just using this information. If there were 5, after they divided, there'd be 10, then 20, and then 40, and hopefully you could probably guess the next one. In a fourth division, there would be 80 cells, and then there'd be 160, and then there would be 320, and 640, and it goes higher. We don't have space for all of that. But I can graph these values. So I'm going to put in, 0, 5, and then I'm going to keep going. So 0, 5, 1, 10, 2, 20, 3, 40, 480, and that's all the space I have. So now if I connect these dots, I get a graph. And got a little wibbly wobbly in there, that's okay. So my graph looks like this. And I can say now this is definitely non-linear. Let's try that again. I don't know where that line came from. Non-linear. It is increasing. Can you give more information? Can you tell me how it's increasing? I mean, this is an okay answer, but we can get better. Is it increasing faster and faster over time, or is it increasing slower and slower over time? Here it's increasing faster and faster. Each time it increases, it's increasing by more and more. Like it increased by 5, it increased by 10, by 20, by 40. Each time it increases, it's increasing more than it did before. So it's increasing faster and faster. It increased fairly slowly here. Look, the slope is not too big. And now at the end, look how steep this slope is. It's really big. So slower to faster. Last of this type for you. If you could please go ahead and pause the video and try this one on your own, and then we will come back together when you're ready to continue. Okay, so X, Y, it says X is our soldiers. It says Y is the amount of plastic left. Okay, factory starts off with 200 pounds of plastic. So I actually have a point. When I've made 0 soldiers, I have 200 pounds of plastic. Now, how much plastic each soldier takes is kind of up to you. If you want to say each soldier takes a pound of plastic, 1 pound, that works. If you want to say each soldier takes 10 pounds of plastic, we don't know how big these soldiers are. They could be really huge soldiers. So it's kind of up to you. It doesn't really say. So I'm going to say each soldier takes 10 pounds of plastic. So 1 soldier, 190 pounds left. 2 soldiers, 180. 3 soldiers, 170. 4 soldiers, 160. 5 soldiers, 150. That's that one. Okay, so let's see here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plastic. I need to get up to 200 pounds of plastic, so I'm going to be counting by 20s here. 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. And now my dots. 0 soldiers. I have 200 pounds of plastic. 1 soldier, I have 190. 2 soldiers, 180. 3 soldiers, 170. 4 soldiers, 160. And you can kind of see the pattern already. 5 soldiers was 150, and I can keep going. 6 soldiers would be 140, and you know what? I can just draw a straight line through these. Boom. We have ourselves an answer. This is linear. This is decreasing. And I'm going to go that extra little step and say it's decreasing at a constant rate. The constant rate means it's linear. The slope remains the same everywhere. Okay. Multiple choice. We've got 2 questions left here. This is the first of them. So this one says, which graph below most likely shows the water usage at a house with X people living there? So let's think about this. As the people in your house goes up, as there's more people living in your house, would you expect the amount of water being used to go up or down? Oh, Probably if there's more people taking showers and using bathrooms and getting drinks and all that other kind of stuff, water for cooking food. So I would expect as the people go up, the water usage to also go up, which would be a positive correlation. Like as one goes up, so does the other, which means not letter A. This one shows as you have more people, they're using less and less water. That makes zero sense at all. Now, between these two, the difference is this one shows that each time you add a person, they use roughly the same amount of water. It goes up by the same amount each time, okay, because this is a constant rate. So each person you add adds roughly the same amount of water. This one shows each time you add a person, you're using an ever increasing amount of water. Like, look at this. This person increases by, like, say, 1 gallon a day or whatever. Over here, after about 5 or 6 people, now it's increasing by 3 gallons a day, adding this person. The next person, or that was 2 gallons. The next person increases by 3 gallons a day. Would the next person increase by 4 gallons a day and the next person by 5 gallons a day? Which of those makes more sense to you? Every single person that joins the house would use about the same amount of water, or each time you add a person, that new person uses more water than the person before them? I think letter B is the right one here, because everybody uses roughly the same amount of water. I mean, going to the bathroom and all that kind of stuff, it's still roughly the same. Yes, some people use more than others. We're not talking about the what ifs. Oh, what if I have a cousin who takes a shower for 45 minutes? Well, we're not talking about that. We're talking about, in general, each person uses the same amount of water. It wouldn't make sense that, I mean, you have one person join the house and they use 1 gallon of water. Or actually, that's about a half a gallon. The next person uses about 1 gallon. The next person is 2. This person over here is using 3 gallons of water. This person over here is using 1, 2, 3, 4, 5, is using 7 gallons of water. This person is using 10 gallons of water. It doesn't make sense that just because you add another person, now you're going from using a half gallon of water a day to somebody's using 10 gallons of water a day. That doesn't make any sense. But that's still a little hard to reason in, and sometimes making a table can be helpful for that. Last question. Which set of labels below most closely matches the graph of the function shown? So here's your graph, and your job is to figure out which of these labels, A, B, C, or D, most likely fits this scenario. Okay, so I want you to pause your video. I want you to go through each of them and see if you can figure out which one most likely shows that graph. All right, so let's see. People in the house versus empty seats on the sofa. Well, if I was making a table for that, I would think if you have one person in the house, let's say you have a big sofa and there's like 6 empty seats. If you have 2 people in the house, you'd have 5 empty seats. If you had 3 people in the house, you'd have 4 empty seats. Like, each person you add in the house just takes up 1 more seat. That would be a linear graph. It's increasing at a constant rate. Every time this goes up by 1, this goes down by 1. This is not showing a nice linear graph. That would look like something like this. Or, you know what? I could even graph these points on here. 1, 2, 3, 4, 5, 6. And it would go down by 1, 1, 1, 1, 1. Something like that. That's not exactly what we're showing here. So I'm going to say it is not letter A. That's linear. Letter B. Friends versus Skittles each person gets when shared. Okay, so let me make a table. If I have 0 friends, sad me, I can get all 100 Skittles. Nah, let's break it down. I'm going to pick a different number. I'm going to pick 24. 24 divides by more. If I have 1 friend, so if I'm sharing with 1 other person, how many Skittles does each person get? Well, you'd have 2 people to share with, you and the friend, so each person would get 12 Skittles. If I have 2 other friends, and I take that 24 divided by all 3 people, or maybe this is a little confusing. Here's 1 person, just me. Here's 2 people, me and my friend. Here's 3 people, me and 2 friends. So if I took that 24 divided by 3 people, I'm going to get, each person gets 8 Skittles. If I divide that same number of Skittles by 4 people, each person gets 6. That graph would look like, I'm trying to make a sketch of this. I'm trying to think here quick. 5, 10, 15, 20, 2, 4, 6, 8, 10. See, counting by 2s doesn't work out so well. 3s, maybe 3. Yeah, 3. Here. 3, 6, 9, 12, 15, 18, 21, 24. 1, 2, 3, 4, 5. All right, so here's 124, 2, 12, 3, 8 would be around here. 4, 6 would be here, and we can see the graph looks like that. It's decreasing, but it's not the curvy's the wrong way. Like this curvy would go like this eventually. I mean, you can see it's kind of slowing over time, where this one's decreasing faster and faster and faster over time. So I don't think that's the right one either. It's decreasing, but its curvy's the wrong way. Letter C, the temperature outside versus number of people in the pool. It's hard to tell. Well, let me think. Well, I mean, like if it's 0 degrees outside, how many people do I expect in the pool? Probably 0 people. Whoa, wait, let's try that again. X, Y. If it's 0 degrees, I expect 0 people in the pool because that's really cold. I don't want to be in the pool when it's cold. If it's let's jump a bit. If it's 80 degrees outside, yeah, 70. 70 is not that warm. I expect a low number of people in the pool. Let's say 50. If it's 80, I expect more people. How about, I don't know, 70 people in the pool? If it's 100 degrees, there'd be a ton of people in the pool. Let's say there's 100 people. The problem with this is showing something that is increasing. This would be like a graph like this or this or this. Like it's increasing, not going down. As the temperature goes up, you're not going to get less and less people in the pool. You're going to get more and more. So this is increasing, not decreasing. So we can't use him, which kind of leaves letter D, time versus height of a plane as it lands. So if I'm talking about a plane as it lands, I mean, I could imagine here's my airplane. Y'all know my beautiful airplane skills. Beautiful. So here's my airplane. And over time, I mean, it's flying, it's coasting. All of a sudden, it's got to go in for a landing, and it's going to decrease faster and faster as it's kind of coming down in for a landing. I can see that. Out of these, now maybe you think that's not a great graph. But out of these other ones, I think that's the closest. Which of labels most closely matches the graph? It's not a straight line. It's not increasing. This one was curving the wrong way. So I'm going to go with letter D. I think that's the one that most closely matches the function shown. Oopsie. Letter D. Last word, or last page here. Could you please pause the video and describe at least 5 words you can use to describe functions? Give 5 of them. Pause the video, come up with 5 words right now, and when you're ready to continue, hit play, and we'll go through it together. All right, so what'd you come up with? I can come up with, increasing, and decreasing, and linear, non-linear, constant. We could say constant rate, which kind of ties in with linear. This constant, by the way, was when your function was just a flat line, horizontal line like this. We'd say that the function is constant. It's not increasing or decreasing. It's kind of staying the same. So here are the 5 words that we used in this lesson to describe different functions. We could say, I have another one. We could say it's increasing, decreasing. We could say faster and faster, or slower and slower. So I know that's not necessarily a word, but it's a more descriptive phrase we could use to describe functions. So I even got a couple extras in there. Good for me. So thank you for watching this lesson on describing functions and understanding functions and their labels and their graphs. Until next time, toodles.